The next chapter in electricity will be variation of resistance with temperature. Now we learned what is resistance. Resistance is the barrier created within a conductor for the flow of electrons. So there are four types of conductors we have to consider: for metallic conductors, semiconductors, insulators or non-conductors, and there's another special conductor called superconductors. All right, so I have already written the notes to save time, and no worries, we'll think of the explanation now. We'll discuss. When it comes to metallic conductors, we all know about metals. Metals consist of positive ions and free electrons. So if you draw a metallic lattice like this, it consists of metallic ions like this and free electrons, correct? Here. So what happens here is the free electrons are abundantly available. So metals usually have low resistance. But when you increase the temperature, when you increase the temperature, more electrons will be released from the from the atom, so that the free electrons. Now in chemistry you might have learned, from an atom, when you supply energy to the atom, the electrons gain the energy and they are released from the atoms, so that there will be free electrons. So when you increase the temperature, the number of free electrons released within the lattice will be high. So that should be reducing the resistance. But what happens is, when at the meantime, when you increase the temperature, these positive ions, since they are fixed at their position, they start oscillating, because they are also absorbing energy. So they start oscillating at higher amplitude, so these electrons cannot travel conveniently or with ease. Hence the resistance will increase. Two things are happening, keep that in mind. More electrons are produced, which should reduce the resistance, but at the meantime, the vibration of the positive ions is it's like a barrier for the flow of electrons. So the latter dominates more. Okay, even though there are more free electrons, the vibration dominates. Hence when there are more free electrons, they can't move faster. So what happens when you increase the temperature? The resistivity or the resistance will increase. So this is the graph you should remember for metallic conductors, and you should know the reason as well. And for a particular metallic conductor, if you take its resistance, now we convinced ourselves that the resistance of metallic conductors will increase. All right, so this is the equation which gives the resistance of a metallic conductor. Now R theta is the resistance of that particular resistor at a particular temperature theta, and R naught, this is R naught, that is the resistance of that resistor at 0 degrees Celsius. And then 1 plus alpha is a coefficient which depends on the material. All right, for copper it will have a different value, for aluminium it will have a different value. That alpha is called temperature coefficient of resistance, and theta is of course the temperature of that conductor. Now when it comes to temperature coefficient of resistance, now what will be the unit? Now alpha theta is added with 1. That means alpha theta does not have dimension. I hope you all can agree with me, because alpha theta is added with 1. So alpha theta is dimensionless. If alpha theta is dimensionless, we know theta is temperature. So whatever, if theta is temperature, so it will have a unit Kelvin or degrees Celsius. Then this should have the reciprocal of that. So the unit, SI unit, not I don't like to use, okay, never mind. SI unit will be Kelvin minus 1. If not, they can use the unit degree Celsius minus 1 as well. But degree Celsius is not SI unit. Remember, it's another unit. Okay, so that is important. We always need to remember. And also the dimensions, it's going to be theta minus 1, because theta is temperature. It has a dimension of theta itself. So alpha should be the reciprocal of that. This is the dimension you might have to know. So it has dimension and unit. You have to be careful, and that those values will be given to you. This is the equation for the resistor of a particular resistor at different temperatures. Using this equation you can find out. Okay, so this is what happens in resistors. This is what happens in metallic conductors. So that portion is done. And then let's go to something called, let's finish insulators next. All right, now what are insulators? Rubber, glass, wood, this kind of material. But even insulators are made of atoms, correct? So when you increase the temperature, what happens is those atoms release more electrons. They release more electrons, but they don't release a lot of electrons. So the resistivity is high initially. With the increase in temperature, since more electrons are released, the resistivity will reduce slightly. It doesn't mean that its resistivity will reduce a lot and it will become a conductor. No, insulators don't conduct electricity. So the resistivity will be very high for insulators, but with increasing temperature, it will reduce a little because more free electrons are released. All right. In semiconductors, it's little different. In semiconductors, we will be learning about semiconductors in electronics. Furthermore, there are two types of semiconductors: intrinsic and extrinsic. But for the time being, we know a semiconductor. If you take a semiconductor, those in semiconductors we have, unlike this, we have atoms connected by covalent bond. Okay, we have covalent bonds and atoms are there. So here also the same thing happens when you increase the temperature. But here there is another charge carrier. Now here the charge carrier is only the free electron, the black color dots I have marked here, they are the free electrons. Okay, but here in semiconductors there's another charge carrier which is called hole. Free electrons and holes. You will learn about this in detail in electronics. So let's skip this for the detail for a while. When you increase the temperature, these charge carriers are produced more in semiconductors. So if you have more electrons, that means less resistivity. Right, now you might have a question. Here the collision is happening. Then won't collisions happen here? Yes, here also the collisions will happen. Here also both happen now. Here more free electrons were released as well as the collisions happen. Who was more dominant here? The collisions between the cations and the electrons were more dominant. Here the production of electrons is more dominant than the collision between the atoms and the electrons. So here the resistivity will reduce with temperature. So at high temperature, semiconductors will have low resistance or low resistivity, but metals at high temperature, they will have high resistance. And for semiconductors also, we use the same equation. We use the same equation if you want to find the resistance at another temperature. But this graph has to go down. Hence, this alpha will be a negative value. Okay, this alpha will be a negative value. This alpha will be a positive value for conductors. Okay, if not, you can make this plus a negative also, but normally they go with the same equation, but this alpha will be a negative value. So when the temperature increases, it's minus, so this will reduce. I hope you understood that. The questions about the semiconductors resistance is very rare using this equation, but it's better to know, safe to know. All right, good. And I think what we discussed for insulators would suffice, because insulators, we don't worry much about them. They don't have much electrons within them, free electrons released. Every conductor, every material has electrons, but we have to focus on free electrons. Only the free electrons are responsible for the conduction of electricity. Remember that. Now we'll move on to the important part, the superconductors. They are very important. Now, so if you think of superconductors, they are also good conductors. Like they are mainly they are metals. All right, superconductors are metals, but they will behave identical to the metals only above a certain temperature. So I have marked that temperature here. That temperature is called, well, mark theta C. Where theta C is called the critical temperature. Okay, different materials have different critical temperatures. Now, commonly used materials for superconductors are mercury. Okay, now when you take mercury is a metal, right? Mercury is a metal, is a very good conductor, Hg. So for mercury, critical temperature is roughly 4 Kelvin. All right, I will explain what this is. The graph is a little different. Now here the resistivity is 0. Okay, the resistivity is 0. That means resistance is also 0 in this region. In this region, we call it the superconducting region. Here it is above that temperature, it will behave as a normal conductor. Even the superconductor. Remember that. Okay. So for mercury, this is the critical temperature. For aluminium, we know aluminium, very common metal we use. For aluminium, the critical temperature is around 1.2 Kelvin. Okay, look at the temperatures. When you say 4 Kelvin, it is minus 269 degrees Celsius. Very, very small temperature. So this superconductivity, you cannot observe it at what do you call that, ordinary or normal temperatures. It will happen only at what do you call that, specific temperature, very, very low temperatures. And there are other materials as well, not only a single metal. There can be a mix of metals and other compounds. Now strontium titanium oxide, there's a material like this. Okay, it's a mix of materials. It has a critical temperature of roughly 15 Kelvin. Okay, so it doesn't necessarily have to be a single metal, it can be other materials as well. So what is special about superconductivity? If someone asks you what is superconductivity, there is a temperature called critical temperature. Below that critical temperature, the resistance of superconductors is zero. They don't have resistance. Okay, but for metallic conductors this graph doesn't go to zero. See, even at zero, when the temperature is zero, it will have at least a small resistance. It will have definitely. Copper, silver, they all have resistance. But superconductors, remember, below that critical temperature their resistance will be zero, which makes them very, very special. Okay, so according to the syllabus you are supposed to know what are the superconducting materials. I have given you some examples, and what are the properties of superconductors and what are the uses of superconductors. Okay, so if you think of properties of superconductors, below critical temperature they have zero resistance. So when the resistance is zero, that means they have the ability of transferring very large currents. When the resistance is high, low current will flow. Yeah, but when the resistance is low, high current will flow. Here the resistance is very small, so a very large current can flow. All right, so that is one property. Because of that large current, we have learned earlier in the magnetic field, when there is a conductor conducting electricity like this, around that conductor magnetic field will be induced. Around that conductor magnetic field will be induced. We have learned, right, the B. And we have even learned the equation for that B, right? B equal mu naught I over 2 pi r, something like that. Yeah. So when this current is very high, the magnetic field induced will be very high. Okay, so that it can create strong magnetic fields. The advantage of that is, imagine this is the wire. Okay, it is in the superconducting situation stage now. You reduce the temperature of aluminum you use to this. How do you reduce the temperature of aluminum like this? You can use cooling agents like nitrogen liquid. So when you use that, it will get frozen and temperature will become so small. Okay, then our aluminum it's in its superconducting nature. Then when you send a current, the current will be very, very large because the resistance is zero. So a very strong magnetic field will be created around it. It can repel any other strong magnet. So this is the property used in electric trains. Okay, between the rail and the wheel of the train there is no contact, because this is magnetized because of the current going through that, and this is also magnet. So the magnet and magnet will repel each other because of strong repulsion. North and north pole will repel each other. Then there is no contact, so train can travel very fast without friction. But there is a disadvantage to that. Why? The safety is not there. So there is a possibility, if there is a accident, the damage will be catastrophic. That problem is there. But anyways, advantage, you can see advantage. And also these superconductors are used in MRI scans. You might have learnt about MRI scans. In those also we use superconductors, because in an MRI scan we need to produce very high strong magnetic fields. So if you want to produce very strong magnetic fields, we can use superconductors. But the downside is strong magnetic fields are harmful for human beings. Alright, so you are supposed to know these things about superconductors. So I have written, for your convenience, I have written all the properties of superconductors. We already discussed. Zero resistance below critical temperature, ability to produce very strong magnetic fields. So because of this, we use superconductors in electric trains and MRI scans. So if they ask for use, you can write these two. Alright, these are the properties. And then they have the ability of repelling magnetic field lines. I will explain what this is. You have a strong magnet, and then this is also a strong magnet. They repel each other. And then the final one, ability of carrying very high persistent currents, because the resistance is zero. So they won't get heated up and they won't get damaged or melt. So that they can carry high currents for a longer period of time. Constant high currents for a longer period of time. Right? So what is this ability of repelling magnetic field lines? Is this now at a temperature, if the temperature is less than critical temperature, imagine a situation like this. So we are at this zone. So let's say this is a superconductor. Okay, now this is a conductor, and I'm looking at it like this. Okay, superconductor. What happens is, if there's a magnetic field already existing in that area, the field lines will not pass through that conductor. This is how the field lines are going to go. because they will be repelled by the magnetic field created by the superconductor. So like this, for example, right? But if the temperature is greater than the critical temperature, what happens is the magnetic field lines can go through the superconductor, because at that temperature it functions just like a normal conductor. Okay, this is what I have meant by the third step. Okay, I hope you can understand. This is what happens. But so for all these things, you should be in this region. Remember that. Okay, so this is a summary of variation of resistance with temperature and superconductors, and I hope it is clear for you.